portal frame design consists of vertical columns with horizontal beams, rafters, cleats, and girts which form a rigid frame. The beams span across the length of the building, creating an open interior space, making it a very popular design structure for large storage facilities. The specifications of the design were to have a structural slab 400mm thick with at least 10 windows, 2 doors, and a mezzanine 4 metres off the ground, covering an area of at least 8 by 5 metres. The spacing between the portal frames must be between 4,500 and 6,000 millimetres. The building length, frame span, and eave height specified are 20, 14, and 10 metres respectively, with the rafter load being 10 kilonewton meters. All concrete must have a compressive strength of 50 megapascals and all steel must be grade 300.
Now we're onto our Revit model. The dimensions of the model were 20 metres length by 40 metres span, as seen in the site plan here. With the spacing between the frames to be 4.5 and 6 metres, we went with 5 metres as you can see here. Sitting on a 400mm concrete slab, along with an eaves height of 10 metres and a 6-degree pitch for the rafters that have a load of 10 kilonewtons per metre. These helped us pick our rafter and column sizes. They were the rafter 305 by 102 by 25 UB, and the columns were 356 by 171 by 44 UB. As you can see here, it's our mezzanine. Section was 14 metres by 5 metres at 4 metres tall, made from a concrete floor of 200mm thick, with a staircase and railing along the edges for safety. We had 16 windows with 8 on the east and west sides, with 4 skylights as our innovative way to let in natural light and save electricity. A normal door and a roller door on the south side of the building can be seen from inside the building here, as well as our mezzanine section. A 3D view of the building shows the 24mm span deck sheeting as the walls and the 40mm clip lock sheeting roof.
With transferring our Revit portal frame structure into SpaceGas, it helped further improve and test the structural design to ensure it was compliant with the AES 4100 standards, as the structure is subjected to loads under conditions found in the A2 wind region. Through extensive analysis, we were able to extract the dead and live loads, the internal and external wind loads, and the internal longitudinal loads from the data exported from the 2D model into an Excel. With the results generated through the linear static analysis tool, the deflection, bending moment, and shear force diagrams was displayed, allowing for further analysis into each combination load. This allowed for clear results for maximum values of differing loads, ultimately visualizing if the portal frame is compliant with the Australian standards.
In the first image, we see the basic structural model designed in SpaceGas, showing all key parameters such as member sizes, spans, and supports. These parameters are aligned with Australian standards to ensure the structural integrity of the model before any loads are applied. In the second image, the same design now includes a live load Q, representing typical imposed loads like occupants or equipment. This load application follows the requirements of Australian standards, ensuring the model reflects real-life scenarios. Finally, in the third image, we see the load settings, including wind load calculations. Since we are designing for Wollongong in the A2 wind region, the wind loads have been applied according to Australian standards, ensuring compliance with local wind pressure requirements.